Unidirectional composites are a very common type of composites with their fibers oriented along the main or longitudinal axis. They have widespread applications and are the basis for analysis of many other types of composites. To model them, one can usually use different arrangement of fibers in the matrix, ranging from a square arrangement to a hexagonal arrangement, or even a random distribution of fibers within the matrix. In this video, I will show you how to set up a hexagonal unit cell arrangement, and I will show you how to create a virtual domain and show simulation results such as these types of uniaxial results as well as shear simulations. So let's sit back as we get started with this modeling. Hello, my name is Dr. Michael Okereke. Welcome to CM Videos. This is a YouTube channel where we try to help you create effective computational modeling solutions to whatever computational problems that you're dealing with. The outline that we're going to be working with in this video includes, first and foremost, defining the hexagonal unit cell. Then we'll talk about how to actually construct this within ABAQUS so that you can understand how to create it. Then we'll now move on to modeling the unit cell within ABAQUS. And then finally, we analyze the simulation results we're getting so that at the end we're able to extract stress and strain data as well as effective properties for this kind of composites. In thinking about the hexagonal unit cell arrangement of the virtual domain, so the virtual domain we're going to be using is a 3D virtual system, which has a cuboidal arrangement with dimensions given like this. So we expect it to be something like this, with the fiber arrangement taking a hexagonal distribution. The material that we're going to be modeling with is a polypropylene material for the metrics with the properties given and the fiber properties also given. I'd like you to know that the diameter of the fiber is 15 microns as specified here. The properties that I'm using for this video are taken from a publication of mine from a few years ago. If this is the kind of content that you like, please, I do encourage you to subscribe to this YouTube channel, so when contents like this are made, you'll be the first to see it. I also want to highlight that there is a CM Videos Insider group, which I regularly send every week newsletters to talk about behind the scene in CM videos and more about products that's available on CM Videos, and also offer my perspective on a lot of computational modeling issues. If you're interested in these kind of things, please do subscribe to this CM Videos Insider group. So thinking about the hexagonal arrangement of fibers, so basically what we want to do first is I'm going to use a circular arrangement. So I'll start with a circle to help define the hexagon. So it's basically a hexagon that is circumscribed inside a circle, inscribed inside a circle as shown here. So you could see the hexagonal arrangement here. The critical point are these points of intersection, because this is where we're going to place the fibers. So if we then think about the angles inside for this regular hexagon will be 60 degrees. So what we then need to do is to circumscribe the circles as shown here. These are the circles taking positions along the edges or the points of intersection of this hexagon. There is a distance we can note here. The diameter of this fibers are df, and there is a distance which is basically the radius of the circumscribed circle. This radius is equal to the same height, the edge length of the circumscribed circle, because in the end this is going to be an equilateral triangle, so this distance s. So the critical thing about this distance s is that there's actually a formula for connecting the diameter to this distance and also the volume fraction. So this is about the packing of the hexagonal arranged fiber. So it takes this kind of formulation, and there's this distance that we need to note, which is the separation between the first row of fibers or the first column of fibers and the central aligned fibers, and that distance can also be calculated based on s. We want to note these numbers because they will feed in to our construction of this virtual domain. Now if we put the numbers that we have, the diameter is 15, the volume fraction we're working with is 35%, and then you get that this distance or the radius of that circumscribed circle is 24.15 microns. And then the distance of separation between the center fibers and the first row of fibers next to it would be 20.91. So we're going to use this all in creating our virtual domain. There may be instances also where we want to double that distance, so we get 48.3, and to double the distance of B, we also get these values. Now, the case study that we're going to study for this simulation first is we're going to load the structure in the main longitudinal fiber direction, which is case 1, and then we'll try two uniaxial transverse directions, which are the case 2 and case 3, and all these are going to be in tensile deformation. Then we'll now switch on to the shear deformation, and we're going to be working on different shear planes. So in the first case will be a shear on the XY plane, and then we'll work with shear on the YZ plane, and finally we'll finish with shear on the ZY. Just a quick question of the day: which fiber distribution pattern do you use in your modeling? Is it an ordered arrangement, a square arrangement, hexagonal arrangement, or even a random arrangement? I would like to know. So tell me in the comment section of this video so that I will know which one you prefer. And also, especially if you want me to do similar videos like this in future, which of these arrangement types do you want me to focus on? Is it the square one, the hexagonal one, the random arrangement ones? What are you interested in? I'd like to know, and I'll see if I can make videos like that to support you. So we're going to go straight into ABAQUS, and then we get started with how to actually create this domain. Okay, so the first thing we need to do is to create a hexagonal arranged fibers. So hex fibers, so we're going to call that, and it's going to be extruded deformable in that. So we need to create a circle, so we know that the diameter of this circle will be this distance of separation for a hexagonal arranged fibers, so that would be 24.1550. So we've got that. Then we need to create the angles of the fibers. So we use this construction line to first tell us which points these things would be. So just randomly position construction lines. Then we make sure that this angle is 30 and this other bit is also 30. Okay, so all the points of intersection here are where the fibers will exist. So we're going to use that. So this point of intersections to define our fiber. So if you again go ahead and implement it this way, so you can see the hexagonal arranged fibers are right there in the middle. So we can then go and say, okay, this is our circle, so it's at 0, 0 and 7.50. So that's the circle. So we're going to have to translate it from here, from where it is, okay, from 0, 0 to that point, and we're going to do it for all of them. So this shows us the hexagonally arranged fibers and everything in place. So to kind of simplify this, we're going to delete all the boundary fibers, all the construction lines, as well as the construction circles. So we have a simple arrangement of this. So we're going to have to pattern it to the top and to the bottom, you know, the way we see fit. So what we're going to do is do a linear pattern. So we select these bottom entities. So we want to create more, so put that number there. So we've got that axis. So we'll do the same for the top. So we'll do a linear pattern, select the top. Now this time around we're going to flip it around, so we got it on that axis. So we've got a sort of an arrangement there. So the next thing we're going to do is to pattern these other ones as well. So what are we going to use? So we're going to use this distance 41.8214. If we click on that, so we select that, this would have to be that distance, which looks perfect. So we'll do the same for the other side. So we'll do a linear pattern of the same system, but this time around we flip it around to this other side. Okay, so we've got a good arrangement of the fibers the way they are. Okay, so how much do we want it? So let's say 120 millimeter is fine. Now, so what we're going to do now that we have the hex fibers is to cut it down to the right shape that we want. Okay, so select the plane we want, select the edge. All right, so we have to now cut it down to the plane we want. So maybe what we can do here is just to get the angles right so that we know exactly what we're trying to do. So basically we just want to have a few of this. So the distance involved will be so we've got what we are interested in. So we've got a system like that. So let's just create what we're looking for. So we start from that corner and we end up here, okay, and then we'll create a bigger box. Okay, so then we can extrude cut. So what we then need to know is how wide apart the systems are in the x-axis. So let's find the distance from this point to that point is 3.64. So we'll do the same from this point to that point. So 72.4. So we're going to then create a matrix based on that. So what is our metric system? So our metric system would start, so half of that. Okay, so we've got the dimensions. So one will be minus and minus 36.218 and then 8. Okay, so we've got the dimension of the matrix and we want it to be as equal as 120. Okay, so we can then create the instances for the two fiber systems. So we can then form the hex to XRVE. We return all the intersections and we get everything in place. So we've got that done. So we can then explore meshing it. So select and use a tetrahedral mesh and then we mesh the domain. So we've got our mesh. So could we reduce the mesh size? So maybe we should do 6. So what we're going to then do is to create the material. So the first thing we have here is our first material would be e-glass, and then polypropylene will be the next one. To e to power 6 at 0, and then 38 e to power 6 at 0.05. Okay, so we've got a plot that looks like this for the polypropylene. So we'll get the sections. So PP section would be, and then e-glass section. Right, so we'll do a section assignment. So first thing we're going to do is to select the middle. Okay, so this is a metric, so the PP section. So what we're going to then do is to select everything and deselect the matrix, leaving the fiber, pressing down shift to deselect. So we now have the e-glass, and then we can look at the material. So we've got it all right and all meshed. So we'll create a few sets. So the first thing is X front. So if we do the X front, so press down shift and hold and select everything independently. So that's the X front. Y top. So press down shift and select everything independently, and you do that for all of them. Okay, so that's the XZ front. So we're going to turn it around. So we've got all parts of the model identified correctly. Okay, so we need to find where to apply our reference point. So first thing we need to do is to find what's one of the corners. So if we find what this point is, so put our reference point close to it. So instead of it being a 41, so why not let's make it a 51. Okay, so we need to create a reference point set. So reference point set, which is that step. So the loading step can be the normal loading step as usual, not a problem. History output, so reference point history output. So this will be associated with the reference point. And we're looking for RF1, RF2, RF3, U1, U2, U3. So the reaction force and the displacement. So those are what we need. Now the next thing is to apply a boundary condition. So X back. So X back as a roller support, initial boundary condition, displacement. So we now need to look for the X back. Highlight it, okay. So fix it in one direction and do the same for the others. So this is fixed in the 2 direction, and then Z back roller support. So this would also be fixed in the 3rd axis. And then we can apply our load. So let's say our load here will be a dismemberment condition, and this will be applied to the reference point. So in the first instance it will be X. So our X-axis has a length of it's 3, so can we do 16 as a displacement, 20% strain? Now we need to consider constraint. So our constraint equation will be equation, and so we're going to say the reference point for this first case would be x front, 1 degree of freedom, 1 degree of freedom with respect to the reference point set, and -1. So what we have done here is that we've connected the displacement of this reference point to the displacement on the front, and this is why we're extracting our history output based on that as well. So I'm just going to rename this and call it my x tens. Okay, so and then we can then create other cases. So if we copy and then create y tens, so with the tensor case, it will be everything will be the same. Our load will not be oriented in one direction, it will now be oriented in the 2 direction, which is the y-axis. Okay, and our constraint equation would now be in the 2 direction, no more on x front but y top. Okay, so then we'll do the same for the z tensor case. So with the z tensor case, our loading will be different. So our load will now be in the third axis, and as a consequence, our constraint equation will also change. So the constraint equation would now be with respect to the third axis, which is a z front. Okay, so it's going to the z front and it's a third axis. So that means as we pull here, we're pulling in the third axis, and every other thing is the same. So those are that. Then why not let us create the shear case? So if we copy to create XY-Shear, so it will require slightly different boundary conditions. So again, look at what's happening with the loading. So in shear, we are sharing on this case XY. So we are sharing in the Y direction, but on the X phase. So constraint will be different. So our constraint equation will be on the X shear in the 2 direction. Okay, so we are sharing in this 2 and in this 2 direction. Boundary condition will be different because we are sharing on the X phase, so X back will change to become X back fixed. Okay, so if it is then fixed, we have to fix it in all 3 directions. All right, and then these 2 would have to be suppressed. And then we need to create a boundary condition for the front. So this will be X front roller. Okay, so roller support in the front. So we'll link that to this front. Now we only allow it to roll so in the other direction. So what we're going to do with the other directions is that we're going to prevent it from moving in the x-axis. Okay, so but it can then move up and down, inside and outside on the x-axis. So the y-axis will be the axis that is free. So we can then basically do that. So this is fine in terms of what's happening on that plane. Okay, so that's our XY shear. So what about YZ shear? So we're copying that, and then we're going to get YZ shear. So with this YZ shear, the same kind of argument would hold. So our loading will be different. So we change the load here so that YZ, it now goes towards the Z axis, but acting on the Y plane. How do we accommodate for the Y plane? Okay, so the constraint equation will be from Y in the Z direction. So still Y, but it moves towards the Z direction. That gives you YZ. Okay, so YZ means that the Y base has to be fixed. So we rename the Y base from a roller support to a fixed support, change its degrees of freedom to constrain it in the X, Y, and Z direction. This other 2 will be suppressed, and then we need to create a Y top roller. Okay, to create a Y top roller, so our Y top now will have to roll YZ, so we constrain it in the Y direction so that it doesn't move up and down, but it will shear in the Z direction. Okay, so that's for YZ. Now the last of them will be the X or ZX or XZ. So copy, so this will be ZX-Shear. So with the ZX-Shear, so the loading will be different as well. So we check the load. The loading would be ZX, so it's going towards the X direction. Okay, so which is kind of what we have here. And ZX, so our constraint equation would be on the Z plane, Z front, okay, ZX, but in the one direction. Okay, so this is what we have, and then ZX, so that means the Z back will become Z fixed. Okay, and if it is fixed, we want to fix it in all three directions. Now the other two will have to be suppressed, and we create another one which is Z front roller. So there will be a roller support at the front, so Z front, and we only constrain it in the X direction. No, so in the Z direction, okay, ZX, so that it can move in the X adequately. So it's moving in the X, but then the loading is acting this way to create that. So this is what you get in terms of the shear deformation. So we've created all these scenarios. We just need to create the job and submit. Okay, so we've created all the load cases, all the scenarios, so we'll just submit them. So we've submitted all of them and they are running now, and we'll now look at the result. Okay, so here is the first result from the simulation, and this is for the uniaxial tensile test along the x-axis. So if we animate this a bit, then you can see what's happening. So basically the structure is being deformed in this way, and what we see here is basically the plastic strain in the model. So the plastic strain in the model, and you can see what's happening. So there's uniform deformation across in every direction. So if we look at the next one, so the next one is a plastic strain in the y direction, the y tensile direction of this, and you can see what's happening here. So you're pulling it in the y direction and the structure is undergoing compression, and then you see a similar kind of behavior as the one we saw before with distributed strain, plastic strain across the domain. So let's look at the Z tensile case. So this is a Z tensile case, and if we animate it a bit, so you can see what's happening again. You're pulling in the fiber dominated direction, and the loading is being sustained mostly by the fibers. So the matrix remains sort of really unstrained. It's a fiber that is taking out the load, and again, this is the advantage of a uniaxial composite. So let's look at then the shear cases. So the next one we see here is the XY-Shear in this model, and it gives you a shear deformation that looks like that. So instantly you can see an accumulation of shear strain as the structure tries to fail at those faces. So if we switch it to the XY plane, so you could see what's going on here. So it shows you an accumulation of shear strain on that faces, and as the structure undergoes a shear deformation in this case. So this case shows us the YZ shear. So you're pulling it in the Z direction on the plane where the Y outward normal is on the Y plane. So you can see what's going again. You're shearing along the fiber axis, and you're getting some kind of interesting result from this. So we can also look at the YZ plane. So it shows the deformation on the YZ plane with the fiber remaining almost intact, exactly the way they are supposed to be. So the last kind of shear is the ZX-Shear. Okay, so here we see the ZX-Shear. So that means you're shearing on this face where the outward normal is the Z-axis, but it's along the Z direction, and you could see a kind of a kinking of the fibers showing here across the domain. So that's the ZX-Shear. So if we look at the ZX plane, you can see what's going on here. So if we just animate it, it could show you how the structure is undergoing a shear in the ZX plane in this case. So that's really the picture of all the shear deformation that we have seen from this simulation. So the final thing we need to do is to go ahead and look at the stress strain data that we can generate from all of them. So the first thing we need to do here is to go back to the XSR case. So based on the XSR case, so we need to use this create XY data history output. So in the XSR case, we already asked the simulation to give us this value. So we're going to extract a reaction force in the one direction and the displacement in the one direction, which is the x-axis. So we plot that, so that gives us a trace of the force profile and the displacement profile. Then what next we are going to do is to export this data. So plug in tools Excel utility, so recurrent plot. So this takes this data into an Excel graph. So if we then open up the Excel graph, it gives you this data. So we're going to copy. Now I've already formatted this file, which I'm going to include in the description section for you to download and use. So basically what we have here is time, reaction force, time, and displacement, so which is the data we copied. So we bring it into this window, and then the next thing we have here is the length of the RVE, which we found is 82.6 micron wide, 72 the width, and then the depth, which is basically the height of the RVE, is 120. So here I'll calculate the Young's modulus and the effective strength. Study this file and then use it for your simulation, for your analysis. So in the first column, obviously this is just the force data that is extracted by here. So basically it's that column. Then the next thing here is the strain data. So what is the strain? Strain is the displacement in the one axis divided by the length on that one axis, the length of the RVE. Okay, so displacement in that axis divided by the length. And then what is the stress? The stress basically is the force divided by the length and the width. So if we go back to ABAQUS, so what we're trying to say is that the force extracted on this plane, remember we linked it to a reference point, the force on this plane divided by the height times the length. So this area, so this is 120 and it's about 72. So this is what we have here. So that gives you this data, and with all that information you apply it across the domain, so it gives you this force data which shows you the measure of the stress and get strain. So I'm going to do the same for a shear case scenario. So this is our XY shear. So we'll go through the same thing. So they create XY data based on the history. So how do we plot the XY data? So on the plane where the outward normal is X is where we apply our displacement. However, we're moving in the Y axis. So the reaction force for shear on the XY plane will be reaction force in the Y axis because it's an XY. So the deformation is along the Y axis. So we're using the reaction force in the Y and the displacement in the Y, and we plot that. So this gives us a trace of the reaction force and the displacement. So again, we export these two data into Excel so that we can then copy that and then open the reference file that we have. So what do we have here? So okay, we've got again the length, the width, the height, and then the Young's modulus calculated. So if we look at what we are doing here with strain, so strain will clearly be the reaction force in the Y, the displacement in the two direction divided by the length of the material. So if you think about what we're doing, so basically you're looking at the displacement here divided by the length of the material. So this is the strain. So this is what we have. The displacement divided by the length gives you the shear strain. Or in other words, tan of that angle of the formation of the shear is equal to the displacement, which we're extracting from the simulation, divided by the length of the RVE. And then what about the shear? So what we're trying to do with the shear is that we're trying to calculate the shear force here, length and the height. So that's the shear. So that's what we have here, and then we apply all that, we get all that. So we can go through all that. So I've already done it for the tensile, the shear, and all the shear scenarios. So the first thing you see here is a comparison showing you the different scenarios. So the Z tension, which is a fiber dominated direction, obviously is very strong and has the highest Young's modulus. And then the other bits are the two here are this Y tension and the X tension. So these are the transverse directions, and all these are the shear cases. So if you look more closely on them, what you will see here would be the same. So these are the transverse cases and these are the shear cases, and the values are there. So if you look at the comparison of the effective properties from this, so in the Z tensile direction, the tensile modulus, the Young's modulus is about the same. There's a slight variation in terms of effective strength, which is sort of expected. The tensile modulus in the z-axis or the fiber dominated direction obviously is high, so this can also be calculated, analytically. And this number doesn't really make sense because we're not allowing the fiber to fail, so it's just an excessive value. And then you end up having a bit of the other values. These are the shear stresses with this. If you have enjoyed this, here is a video about RVE modeling of a UD composite with random arrangement of fibers. Another video that tells you the effect of sizes in terms of the RVE modeling. Thank you for your interest in this channel, and I'll see you in the next video. Bye bye.